Good morning, everyone. Thank you so much for taking the time to attend our webinar. We have a very important topic today. We're going to be talking about GitHub Actions and how to avoid vulnerable configurations that could lead to code injection. Our presenter is Alex Ilgayev. He is a security researcher here at SciCode, and we will be taking questions at the end of the presentation. Please feel free to ask questions at any time, and we will address as many of them as we can at the end of the presentation. So thank you very much, Alex. The floor is yours.
Thank you very much, Andrew. So as you introduced me, today's webinar topic will be GitHub Action and code injection and how to avoid vulnerable configurations. So during our next 25 and so minutes, we'll present our latest unique research on the possible code injections on GitHub Actions. So let's start with the agenda. During the talk, we'll explore, first of all, what is GitHub Actions and why it is a powerful build system. Later, we'll learn what kind of misconfigurations it can have and how an attacker can leverage this into a code execution. Then we'll explore the risks of a compromised pipeline, including 2 demos. And at the end, we'll learn how can we mitigate these issues. So I'm Alex Ilgayev, a senior security researcher at SciCode. Previously, I were investigating malware threats and campaigns at Checkpoint Research. I love anything that relates to security and hacking, so don't hesitate to reach out at me through Twitter. So first, what is GitHub Actions? For most of its history, GitHub was all about storing source code. In 2018, they announced that they are going in a different but related direction, but by launching GitHub Actions, a CI/CD platform, continuous integration, continuous deployment, allowing GitHub developers to automate development workflow easily. Since then, GitHub Actions have become extremely popular, mainly due to its rich marketplace containing more than 12,000 actions and free hosted runners for public repositories. By now, GitHub has over 73 million developers and more than 200 million repositories. Almost any language or environment has an action that helps you to automate the workflows for that environment. Before we go deeper into the misconfigurations we found, let's understand first the possible usages of GitHub Actions. Some of the usages may be building the code into a container and uploading to the chosen registry. This could be Docker Hub, Artifactory, ECR, GCR, or any other registry. It could be creating scheduled tasks that scan vulnerability in code. It could be running tests for pull requests. It could be automatic labeling for issues based on predefined logic. It could be sending issues into a ticket handling system like Jira, Monday, Asana, etc., and much, much more. So how does GitHub Actions workflow looks like? First of all, it's a YAML file, and it contains a name, a triggered event when this workflow will run. In this example, the event is a push to the repository. So on every push into the GitHub repository, we will run this action. And lastly, the jobs that it should run. In this example, we have one job that is called Actions Hello World that should be run on Ubuntu machine and has one step that echoes Hello World. And that's it. That's simple as it sounds. To understand the vulnerabilities, we need first to understand some core mechanics of GitHub Actions. The entity that runs the job is called GitHub Runner. This runner is an open source code that fetches the job from GitHub Actions service and executes them. This runner could run either on a GitHub hosted machine, which is the more popular solution for most of the GitHub Actions, or it could also run on a self-hosted machine. If you choose to use the GitHub hosted machine, so it also runs as an ephemeral environment. This means that each job will run on a completely clean VM isolated machine, and once the job is over, the environment will be completely deleted. This is a security measures that GitHub Actions introduced. In addition, for each job, GitHub creates a temporary token that is called a GitHub token, which can be used to access the GitHub API for various tasks. Such tasks could be updating issues, comments, pull requests, code, and more. Another interesting topic is that the default permissions for the GitHub token are read and write for most of the triggered events. Another core mechanic of GitHub Actions is secrets. Using secrets is an integral part of creating a meaningful GitHub Actions workflow. Example for such secrets could be cloud tokens such as AWS, GCP, Azure. It could be artifact registry tokens such as Docker Hub, Artifactory, and etc. GitHub separates secrets to 3 layers of exposure: organization, repository, and repository environment. Secrets defined in organizations will be exposed to the all repository and all the actions in that organizations. But in addition, you could configure these secrets to be exposed to limited repositories, either to all the private ones or specific ones. Secrets defined in a repository are exposed to all the actions in that specific repository. And in addition, we have secrets defined in the repository environment, which is a more secure method to use secrets, which we'll talk at the end in the mitigations part. Now that we learned what is GitHub Actions and why is it a powerful system to build pipelines, let's understand what is code injections. We created a sample workflow that does the following. It is called issue check. It will be triggered whenever a new issue on GitHub is created. Usually you create issues either on bugs or a future request for the product, or there are many more usages for it. And the job of this workflow will be this bash script, which checks the title of the issue. And if the title contains the word bug, so what it does, it will go to GitHub API and it will add a label called bug to the issue. This could potentially help the maintainers of the repository to prioritize issues. So in this workflow, we can see these curly brackets, which is another mechanism of GitHub Actions. This allows workflow developers to use additional information that comes from triggered events. In this example, we have several such usages, such as in this case where we fetch the title of the issue which triggered the event. The second usage is here, where we're using the GitHub token, which we talked about previously, to issue the API request to GitHub. And the third usage is here, where we're retrieving the issue URL, so will know what issue we should add the label to it. So on a first sight, this workflow looks innocent, but a malicious title could actually alter this bash script and run and control code. For example, if we create an issue which looks like this, we actually injected a bash script into that code, and we managed to execute code and print this pretty psycho text. So we actually have code execution capability on the pipeline runner. So you may think this is a bug, but not only it's not a bug, it's even mentioned in GitHub documentations. It says that when you create workflows, you should always consider whether your code might execute untrusted input from the attackers. So we went and discovered if this is a really issue in the open source community, and our research shows that this is an extremely widespread issue. The amount of repositories vulnerable to such injection was really tremendous. We identified dozens of repositories which share this vulnerability in their GitHub Actions workflow. For each such repository, we reported it to the maintainers and they fixed it almost immediately. Out of these dozens of repositories, you can observe the most popular ones. That list contains Liquibase, which is a popular tool to deploy database schema changes. A Dynamo, which is a visual programming tool that is sponsored by Autodesk. A Fauna, which is a transactional database. A Wire, which is an open source communication platform. Astro, which is a static site builder, and more. If we sum the users of all these tools, we could really reach millions of potential victims. So the consequences of such build compromise can be quite disastrous. The first major impact is exposing the secrets of the vulnerable workflow. As we previously introduced, such secrets could be cloud tokens and additional assets. The second major impact would be the ability of the attacker to commit malicious code into the repository without proper permissions. This can cause a critical supply chain incidents, as the attacker can introduce various vectors which will be built into the product and deployed into end user or organization environments. A much smaller risk would be the malicious actor's ability to run botnets or crypto miners using runner infrastructure. So to demonstrate the ability of the attacker to expose secrets, we created an intentional vulnerable workflow, which will follow us in the example. This workflow will be triggered when a new issue is created, as we showed previously. In addition, we also defined the GitHub token as an environment variable for the runner. And it has one job that's called vuln job that has 3 steps. The first step is doing checkout. This is the syntax of calling an external action. And it's using the action they call checkout, which is one of the popular actions in the marketplace that basically does git clone to the repository into the runner environment. The second command will be printing the issue title and the body. And the third run command would be issuing a request to GitHub API and adding a label to the issue that's called new issue. So as we showed previously, these both steps are vulnerable to code injections because we are not sanitizing this user-controlled input. So let's assume, this means that the attacker could compromise that build workflow in this exact step. So let's assume the attacker can execute any code he wants in this step and explore how can he get any secrets from this code execution. The first part is the environment variable definition. Because we define the GitHub token, which is a temporary token created by GitHub for this workflow, in this environment variable, if attacker will be able to execute code after he managed to get execution capabilities, he could just print the environment variables and extract this token. So he could extract the token using this code. This is simple. The second possible method would be because of using checkout. We don't see it here, but behind the scenes, when we call this action, we're actually sending default parameters, which one of the default parameters is this GitHub token. So it's sent into the action. Also, when we are cloning a repository, we're also saving the credentials in the .git/config file. So if the attacker, when executing his code, want to extract the GitHub token, he could fetch this .git/config file. And after he base64 decode it, he will get the exact GitHub token, which he could use to his malicious purposes. The third method is a bit more complex. During our research, we understood that each such run command is written into a shell file before it's been executed. For example, if the attacker wants to fetch, if he will fetch this file, he will receive the exact run step that we'll see here, but instead of the placeholder with the double curly brackets, it will have the actual value that inserted as part of the event. So if we, in our example, we want to fetch this secret bot token from the final run command, if we'll be able to get this script in that directory, it will contain also this bot token, which we could use it as an attacker. But we said that the attacker executed code in this command. So how will you get this command which happens after it? So one method you could apply is to put a persistent script on the runner and monitor this runner temp directory, that whenever a new shell file will be written, you could send it to a control server. And we'll see how it's been executed in the demo. In addition, we could apply additional, more advanced method, which we won't cover in this talk, like examining the memory, examining processes, and etc. So let's see the two demos we said we will have. The first demo, on the left side, we're going to see the attacker controlled server, and we'll simulate an attacker controlled server. And on the right side, we have the victim repository. So at the start, we are setting the server. And now we are sending the malicious issue to the victim repository. This issue actually runs several commands, and it will exfiltrate the secrets in two steps. The first step, you can see we exfiltrated the GitHub token, and then we put the persistent script in the runner, and we managed to exfiltrate the second token. You could see that we'll see here the complete script, which was the third run step in that sample workflow. This script also contains the bot token which the attacker wanted to exfiltrate. So the second demo will show how can the attacker commit malicious backdoor to the repository without the proper permissions. So at the start, we have a sample repository which contains 2 files. Then we're creating a new issue. This issue contains several commands. The first one, we're fetching a malicious script from a remote URL, and then we're fetching the malicious file which we want to commit into the repository. Then we give the right permissions to the script, and we run in the script. We could see that after we run it, we have an additional file in the repository which the attacker committed. A more advanced attacker could do this also without leaving any trace and remain pseudo. So after we show what possible consequences of a built pipeline compromise, now let's see how to mitigate it. We have several possible mitigations which we could apply to stop such attacks. The first one is avoiding run steps. For example, instead of running curl command, this is a bash script. Instead of running curl inside a bash script to update a label like we did in our example, we can use an external action. In this example, it's called labeler, that is doing exactly the same. It receives the parameter of the label name, and it does behind the scene this call. But this method is more secure because you can't inject into an action. Second method, and the most effective for this, in our case, is sanitizing the inputs. For example, instead of putting the curly brackets in the run script and putting our user-controlled input there, we could define this outside of the run script and define it as in external environment variables, and then use these variables inside the run script. In this case, even if this title or body will contain malicious code, this code won't run. The third method will be limiting token permissions. We can add to our workflow tags like this, which are called permissions, which will indicate the maximum level of permissions which the GitHub token will have. In our case, we only need to update the label, so we don't need write permissions for contents, and need only write permissions for the issues. So if we add these permission tags, even if we have code injection vulnerability in our workflow, the attacker won't be able to commit in the repository because his GitHub token won't have the proper permission for it. Another method is limiting secret exposure. As we said previously, when we were defining secrets on the organization level, we can select what exposure level each secrets will have. We can expose it to all the repositories, which is the less recommended method. We can expose it only to private ones or to selected repositories. Another method is to require approval for outside collaborators. The default behavior of GitHub is to require approval for first-time contributors, which is effective, but we suggest to use require approval for all outside collaborators for a more robust defense. And the last method will be to use environments and branch protections. There's a feature in GitHub that you can define environments for a repository. Environments such as testing, staging, production, and etc. Each such environment could have its defined secrets, but also you can limit the environment to specific GitHub branches. For example, the main branch. But if that main branch will also have branch protections rules, which will protect it like from doing a direct commit into the branch. So you actually securing the secrets of that environment. Okay, so what will be the takeaway from this talk? First of all, even when GitHub does most of the work for handling the build pipeline for you, including ephemeral environments and VM-based isolation, we are showing here that it still can be compromised. Second one, as we've seen GitHub best practices paper, it delegates some of the responsibilities from securing the workflows to the developers. But we know the developers make mistakes, so this should be handled carefully. The third one is that we could see that the consequences of build compromise are quite disastrous and could expose sensitive secrets or cause a potential supply chain attack by committing to the repository. And the last one, which is the most important one, is that GitHub gives you the tools for securing the build, such as limiting permissions and secrets, sanitizing input variables, and more. We highly suggest you to use them. So that's it. You are welcome to check out the full blog post in the link below. And thank you for listening. And I will check if we have any questions.
Hi, Alex. We do have a couple of questions. So as we shift over to Q&A, obviously, please feel free to ask more, but a couple have come through during the presentation, so we will start with those. And the first question is, will we get the webinar on video? And yes, give us a day, possibly two, and we will process and archive this webinar on sitecode.com, and we will send everyone a direct link to that video when it is live. And let's see here. There are other questions. The next question is says, how long did it take you to conduct this research?
Quite short, actually. It about 2 weeks. The point is, once I spotted this pitfall in the GitHub documentation, the possibility of the code injections, it was actually I was able to find vulnerable repositories quite fast, even in few days. So that's how disastrous this issue is. So it's about 2 weeks, I would say.
Okay. And then the next question is, what do you suggest my company does immediately following this research? And I think what they're saying is, what are the most important mitigation steps?
Well, first of all, you should understand what your risks are. If you're using GitHub Actions, which there's a high possibility that you are using it, you should check the mitigations that we are showed here, and we'll check what your organization status regarding it, whether you're allowing outside contributors or limiting permissions or your secret exposures. I would say that you go over the mitigations one by one and just apply them. It's pretty easy to apply them, and they're highly effective. So I highly suggest to do that.
And we don't have any other questions from the audience, but I have one that I just thought of that is sort of interesting. Why is it that you think? Why do you think GitHub itself hasn't made changes to eliminate the risks here? Why don't they just create a patch?
That's a pretty good question. But it has also a simple answer. They just can't. I mean, anyone who understands computer programming and software engineering will is knowing that there's injections in almost anywhere, and they just can't stop it. They're allowing code execution by design in the GitHub Actions using that run command. And even if they will stop specific patterns of code injections, attacker will always find a way to bypass it. So they are not even trying to stop it because it's not really possible in terms of engineering. So they're doing the best they can by advising to be alert for this.
All right, and we just got another question. This one says, one of your bash fragments had a dollar sign in it. Something dot something expression. Is this something Git pre-processes?
Oh yeah, this is the double curly brackets. Yeah,
Yes.
it's not something related to Git. It's more related to GitHub Actions. I mean, it's part of the GitHub Actions syntax. So when I'm writing GitHub Actions workflow, I'm putting this syntax, and the GitHub Actions service that in charge of provisioning these workflows and running them is in charge of replacing this something something with the real value before it's been executed on the runner. So it's explicit GitHub Actions syntax that allows workflow developers to use additional input variables like the issue's title or issue body and more. I hope it answered the questions.
All right, well, those are all the questions that we have. So we will go ahead and wrap the webinar up now. Thank you everyone for your time. This is a very important issue. We appreciate your attention and look forward to, our next webinar coming up next month. Thanks again. Goodbye.
Thank you, guys. Goodbye.